Okay, hello everyone. Welcome to the next CPPC seminar. Today we have Kenny Ng from the Chinese University of Hong Kong. So Kenny did his PhD at the Ohio State University at the CCAPP before having postdocs at Weizmann and Grappa. But he's now a faculty member at the University of Hong Kong. So Kenny is really an expert in dark matter indirect detection. Which is presumably what he's going to tell us today about. So thank you very much for being with us, Kenny, and take it away.
Thank you very much, Ciaran. Just want to make sure so you guys can hear me clearly, right?
Yeah.
Yeah, okay. Thanks very much for giving me this opportunity to discuss my research with you. So I already told Ciaran that TEFPA 2019 was the last conference that I went to before the whole lockdown business. So I really miss traveling, and so I still have fond memories of CME burned in my head. Hopefully we will be allowed to travel soon, okay? And then I really want to visit Australia again. So today I'm going to talk about searching for dark matter with X-rays. Okay. So for this audience, I think I don't need to do too much introduction. So from large scale, very large scale observations, such as BBN, cosmic microwave background, to medium large scales, such as galaxy clusters, and even down to the local inside galaxy scales, for example, from the dynamic motions of our Milky Way. We have many evidence that the known substance of matter or matters that we can directly observe cannot explain all these gravitational phenomena. Okay, so these are the evidence of dark matter. So our own standard model particles cannot account for these observed phenomena. So obviously, one way to solve this problem is that we add a new species of particles, one that contribute quite a lot of total matter density in the universe, and they could explain all these missing gravity. Okay. But unfortunately, so far, all the evidence are from gravity. Okay. So we do not really know the particle identities of these dark matter. There has been a lot of attempts to identify dark matter and identify its particle identities. There are three main approaches. One is so-called direct detection. You build a detector, you hide it underground to shield it from external disturbance, and you hope a dark matter comes in and scatter one of these particles, and then you can detect, for example, dark matter and nucleon couplings. Okay. Another approach is we look at our most expensive machine particle experiment ever built, and we try to collide particles, and some of these interactions may produce dark matter as missing energy signatures. Another way, the final way, is called indirect detections. Okay. So the idea is relatively simple. We know that dark matter exists in the universe, and they cluster around us in the galaxy. So we're looking for two types of interactions. One possibility is dark matter contacting each other, and then they annihilate and they produce something that's visible. Alternatively, dark matter may have a finite lifetime, so they can just decay into some visible matter. Okay, regardless of which way, okay, the main idea is to detect these visible particles. Okay, then we will learn something about whether it's dark matter annihilation or dark matter decay. And through these messengers, we can also identify the couplings and dark matter mass, etc. So indirect detection, compared to the other two, is actually my favorite way of identifying dark matter, because it not only depends on the particle physics of dark matter, for example, what the dark matter decay lifetime, dark matter mass, and how dark matter, which standard model particle dark matter couples to. Indirect detection also depends a lot on the astrophysics of dark matter, right? How dark matter is distributed around our galaxy, or how is it distributed in external galaxies, etc., etc. Okay. So the dream is that once we can do indirect detection of dark matter, we not only identify dark matter, but we can sort of use dark matter and the decay or annihilation products to do astrophysics. And that may significantly improve, right, how the structure of our universe form. As currently, the structural formation is dominated by dark matter, but there's no real good way to directly observe that. So today, the focus of my talk will be on X-ray band. Okay. So these are just some examples of the current existing X-ray telescopes. And you can see that, for example, for Chandra and xmm-newton, okay, one is a US-driven machine and one is a European-driven machine. They've been running for more than 20 years. So there's a lot of data that's already collected, and it allows us to do very, very sensitive search of dark matter. So we're looking for dark matter in the X-rays, and of course then means we are looking for a dark matter candidates that can produce signatures in X-ray. So today I'll focus one of them called sterile neutrino dark matter. It's a very well motivated candidate. Okay. So if the sterile neutrino dark matter is at around keV mass, then what happens is that through a tiny mixing with standard model active neutrinos, okay, the heavier sterile neutrino can decay, can undergo a two-body decay into a active neutrino and a photon, okay, through this loop, and through this tiny mixing with active neutrinos. So this is a two-body decay, and we know that in the two-body decay, this photon will be monoenergetic with energy exactly half of the dark matter mass. So the signatures of these sterile neutrino dark matter decays give you a very narrow and sharp photon line. This is what we like to call smoking gun signatures, because it allows you to identify, right, in principle, the mass of the dark matter, and also allows you to potentially separate from background very, very well. Okay. Of course, very soon you will see a lot of caveats from these nice theoretical expectations. Okay. So for the rest of the talk, I will focus on sterile neutrino. Okay, but most of my discussions applies to other types of dark matter candidates that can also produce X-ray lines, but I would not focus on them. But it's important to know that not only sterile neutrino dark matter can produce X-ray lines. Okay. So a nice dark matter candidate obviously not only gives you a detectable signature, but it can have a coherent story of how this dark matter comes to be. Okay. So for sterile neutrino, we want to answer how they are produced in the first place. Okay. So one famous scenario for the production of sterile neutrino dark matter is the Ludolson-Ridgel scenario. Okay. They realized if there is a tiny mixing between the sterile neutrinos and active neutrino, then in the early universe, when the active neutrinos are still coupled to standard model particles, when they were in thermal equilibrium, then a lot of these interactions is happening. Okay? And through this tiny mixing, sometimes these active neutrinos become a sterile neutrino. Okay? Then slowly these interactions happen and you build up a population of dark matter sterile neutrinos that's immediately decoupled with the universe because they have much weaker scattering strength. Okay? So this is one scenario to produce sterile neutrino dark matter, and this is called non-resonant production. It's very nice because you can show that with a proper mass range, okay, these dark matter are warm dark matter. They can potentially solve some of the structural formation problems right now we are having with CDM cosmology. Okay. And a few years later, people realized, okay, if there is a primordial lepton asymmetry, you can hide a lot of it in the neutrino sector. Okay? Then the effective mixing in here is modified. It's kind of similar to the MSW effect happening in the sun. Okay? So then even with a smaller mixing angle, you can through this resonant effects, you can still produce a lot of dark matter, okay, with a much smaller mixing angle. An interesting fact with this particular production mode is that the produced dark matter, it could be warm or it could be less warm. Okay? This sort of helps you to solve sometimes the dark matter produced too warm and it becomes inconsistent with the observation. And of course, these are not the only two ways to produce sterile neutrino dark matter. Okay, they could come from decays of heavy particles, and I will not focus on these scenarios. So sterile neutrinos dark matter is quite nice because people have successfully constructed a framework, okay, where it is possible to simultaneously explain the phenomena of dark matter, the generation of small neutrino mass, as well as leptogenesis, okay, which explains the barrier asymmetry of the universe under the same framework. So I would say sterile neutrino dark matter is one of the more well-motivated dark matter candidates out there. Okay. Now, this is the parameter space. Okay, we'll see this plot a lot. So I'm going to explain it to you. This is the parameter space of sterile neutrino dark matter. Okay. In the x-axis, you have the dark matter mass. Okay. You can see that it's around keV range. So the photon energy line that we're looking at is also in the keV energy range. In the y-axis is the mixing between the sterile neutrino and the active neutrinos. Okay. So this line here, this black thick line here, corresponds to the non-resonant production scenario. Okay. So if this sterile neutrino lives on this line, then you can produce exactly the observed dark matter abundance. Okay. That also means above this line, it's not allowed because you produce too much dark matter. Okay. Now below this line, okay, resonant production can no longer, non-resonant production can no longer give you enough dark matter. Okay. But there is a range of parameter space that through resonant production, okay, so through the MSW-like effect, you can still produce the observed dark matter abundance. Okay. So I would say sterile neutrino lives in this parameter space. Okay. But there's a limit because BBN limits the lepton asymmetry. Okay. So if the lepton if the mixing angle falls below this line, okay, not even resonant production can give you enough dark matter abundance. Okay, so sterile neutrino sort of lives in here. Okay, of course, if you say this sterile neutrino dark matter is produced by some other mechanisms, okay, then you can relax this bound. Okay. Now inside this parameter space, there's two main constraints that I put it here. One is the X-ray search. Okay. I already told you sterile neutrino can decay into a photon. From the non-observation of those photons, you can put a limit on the mixing angle. Okay. So this is just showing you a bunch of X-ray constraints collected here. Now, if sterile neutrino dark matter is too light, okay, for example, if it's around a few keV, these sterile neutrino, these dark matters are warm dark matter, okay, so they can erase small-scale structural formation. And if they're too warm, then it's not allowed. Okay. So these are the current existing constraints from structural formation. You bound the sterile neutrino dark matter parameter space on the left-hand side. Okay. So this basically summarized the whole situation. And sterile neutrino dark matter, I like it very much because you can see there's a well-defined parameter space bound from all sides. That means if you can test all these white space, then you can forget about sterile neutrinos, at least in this particular scenario. Okay. So I like this a lot, okay, because it gives you a definite target to shoot for. So for the rest of the talk, I'm going to tell you how what people have been doing to try to close this window using X-ray observations. Now, a few years ago, sterile neutrino got a lot of attention because there was a claimed detection, okay, at 3.5 keV in photon energy, okay, from a stacked galaxy cluster observations. So galaxy clusters are giant structure, clumps of dark matter. So these people, and I'm sorry, I forgot to add the reference, okay. So these people, so Bobo et al. In 2014, they looked at a series of galaxy clusters. When they stack them all together, and they try to model their emission spectra as best as they could, and they find a tiny excess at around 3.5 keV photon energy. Okay. So they claim they couldn't find a normal astrophysical explanation for this. Okay, so that means it is possible that this is a signature of dark matter emission. Okay. So that would correspond to a dark matter having mass around 7 keV. Okay. So the corresponding mixing angle they found, it's around 10 to the minus 10, 10 to the minus 10 to 10 to the minus 11. Okay. All right, so this is from one group, and typically we're not super excited if one group claims that they have found dark matter. But very soon, another group of people, so Boyarsky et al. From 2014, okay, they look at a different place. Say they look at the center of M31 galaxy, so the Andromeda galaxy near next to us. And they found a similar excess, okay, with a similar mixing angle strength, okay, from M31. Okay, so now this gets people excited because you have two groups of people looking at two different places, and they can find a consistent dark matter, potentially consistent dark matter signal. Okay, so it generated a lot of excitement. So there are many follow-up observation studies and also proposed models to try to account for this dark matter. So the situation lasted for some time, okay? But for the folks that want this to be dark matter, okay, so there are some recent papers kind of put the dark matter interpretation in doubt, okay? So I will spend some time to discuss what exactly they did, okay? And then I'll tell you what I think about their results. Okay, so one of them is from the end of 2018 by Desert, Broad, and Safdie. So what they did is that they collected a lot of xmm-newton data, okay, and they analyzed them all together. So they performed a joint likelihood analysis. And this is the limits that they set, okay? And you can see that at around 7 keV dark matter mass, they are reaching 10 to the minus 12. So it's one order of magnitude below what people claim the dark matter parameter space lives in. Okay. But, okay, so there are some criticisms about this work. One is that they assumed a very simple background. Okay, they assumed a power law background when they did this analysis. Okay, and these are not, in my opinion, not necessarily true. Okay, another criticism is that they only consider a very narrow energy window around this dark matter mass. Okay, so this simplifies the analysis, but they also neglected some potential effects. For example, maybe there is an extra non-polar emission coming from outside of this energy window. Okay, and that could affect significantly their results. So these, once this paper came out, okay, so then there are two papers that sort of came out criticizing this work. Basically the same reasons that I just mentioned, okay? And of course they replied. And at the end, when they take into account the potential effects of narrowing this window, of only considering this narrow windows, what they found was that the limit could be weakened by a factor of few. Okay. So this shows that this analysis, okay, could have a relatively large systematic effect that's not accounted. Okay. Now, the latest news is by a similar group of people. Okay, so Foster et al., Benek Roth and Safdie above, and research is also here. This is in my opinion, much more robust analysis. Okay. So they consider even more data from xmm-newton. Basically, they collected all the possible xmm data. Okay, they stack off them. They sort of gave up how to model them individually. Okay? But they use a quite nice, quite innovative approach, the Gaussian process, to model, okay, the potential deviations of the data once they subtracted using a background region. Okay, so I'm not going to into details about this. Okay, but so this is a plot showing at the end what happens. Okay, so the blue line, okay, is the Foster et al. So the results from the paper a couple months ago. Okay. And then the orange and the green line. Okay, so the orange line is the original Desert et al. Paper, so the science paper constraints. They are very strong. They went down to 10 to the minus 12. Okay, but once they corrected for potential contaminations from outside of their small energy windows. Okay, so this green region, green line, is their constraint. Okay, and this constraint is very similar to the blue line. Okay, so the latest, in my opinion, more robust analysis. Okay, using the Gaussian process. So I would say these results are relatively robust. Okay, so then you can see, okay, around here, the constraint is maybe a factor of 3 to 4 below the claimed detection region. Okay. So to me, this is showing that maybe this is not really a dark matter interpretation on this. Okay, is in doubt. Okay. Or maybe the simple sterile neutrino dark matter interpretation is not enough. Okay. So what is 3.5 kV line? Okay, so some people have claimed a very significant detection, more than 4 sigma. There are many solutions that's offered. Okay, maybe it's a new, never discovered before astrophysical line. Maybe it came up because we misunderstood our astrophysics. Okay, so it's mismodeled. Okay, or maybe it has something to do with particle physics. Okay. Some dark matter, some dark matter candidates, for example, axion-like particles, they're more favorably converted into a photon line when in a larger magnetic field environment. So that means from different places, for example, galaxy clusters have stronger magnetic fields, the line emission is stronger, and that's why you don't see them in our galaxy. Okay. So this is, I would say, okay, given the recent developments, the 3.5 kV line in the dark matter interpretation of 3.5 kV line is now in question. Okay. Then what's next? Okay. So today I will tell you two works that I'm closely involved. Okay. One is that we aim to close the remaining sterile neutrino dark matter window with an instrument called NuSTAR. Another is how to make a dark matter line search even more sensitive, okay, through a technical velocity spectroscopy. Okay, so I will talk about velocity spectroscopy first. So back when the 3.5 kV line situation is still more unclear, okay, there was really a lot of hope on one instrument called Astro-H or Hitomi. Okay, so it's a Japanese X-ray mission It was scheduled to launch in February 2016. We had a lot of hope in it because one of its instruments have a really, really good energy resolution. Okay, so 10 to the minus 3 in terms of relative energy resolution. So it's more than 10 times better than existing instrument. So having a good line and energy resolution is important for a dark matter line search. Okay, as you can imagine, that allows you to cleanly separate contaminations from astrophysical lines. Okay, but unfortunately, right after AstroX was launched, okay, so there was a software that kind of spins up the rotation of the satellite in space. Okay, so it disintegrated very shortly. Okay. So we did not get a lot of very useful data from AstroX. But there's hope. Okay, so the successor of AstroH is already planned. Okay, so the latest news that I got out from them is they're expected to launch the CRISM mission. So it's a simplified AstroH, but still with the high resolution detector. So it's expected to launch in the fiscal year 2022. So that means 2022 to 2023. So that means potentially very soon, we will have a very, very powerful dark matter line search detector in space again. Okay. Now, with a good energy resolution like AstroH or CRISM, there's one thing one can start to do. Okay, because with 10 to the minus 3 energy resolutions, that means you are sensitive to dark matter motions around a couple of 100 kilometers per second. Okay, with that good of an energy resolution. And that is exactly the typical dark matter velocity in our galaxy. Okay. So that means with a dark matter decaying into a line, okay, with a good energy resolution detector, you can potentially see the movement. So let me tell you exactly what I mean. Okay. So imagine, okay, you have such a good detector. Okay. Now consider this scenario. So this is a picture of our galaxy. So we are located in the sun. Okay, so these are baryonic matters in our galaxy. Okay, so we are co-rotating with this Milky Way disk. Okay, we are sitting inside this plane of baryonic matter. Now, if I look at the left-hand side of the galaxy, okay, so I'm looking at some gas particles around here. Okay. Now, let's say I detected a line in my detector. Okay, and if these lines are produced by gas particles through normal astrophysical process. Okay, so then that means you can see the relatively Doppler shift, okay, from the motion, combined motion of this gas particle and the sun, okay, which is us. Okay, so if you look at this picture, okay, you combine the factor, you will find that this gas particle is effectively leaving away from you. Okay, so you will see a redshifted emission line. Okay, if the this gas particle emits a line. Okay. If you look at the left-hand side of the galaxy. Now, what happens if the line is produced by dark matter? Okay. We're again looking at the left-hand side of the galaxy. So dark matter is different to baryonic matter in our galaxy in the sense that it's not in a co-rotating, okay, with us. Okay. So the dark matter particle motions, so it's moving constantly, but at each given point in the dark matter halo, okay, so there's no preferred direction of motion. Okay. So the mean velocity at this point is 0. Okay. So that means if from this spatial region, the dark matter decays into photon line, and we observe them, due to only our motion, we will see a blue shifted line. Okay, so that means from the same space, a astrophysical emission gives you a redshifted line, but a dark matter emission gives you a blue shifted line. Okay, so you can use, that means potentially you can use this to distinguish very, very clearly two different emission mechanisms. Okay. So I'm just in one more detail. So if you write down the math, once your dark matter signal depends on the particle motion, okay, you will have an extra term that shows that describes the line shift, okay, due to the relative motion, the exact effect that I just described. But there's also another effect that's showed up in the line dispersion. So how wide the line it is. Okay? And that potentially, that depends on if it's astrophysical emission on the gas temperature. If it's dark matter emission, that tells you the dark matter velocity dispersion, okay, which reflects the Milky Way gravitational potential. Okay. So these are the two new effects one can potentially see, okay, if we have such a good resolution detector and if dark matter gives you a line. Okay. All right, now go back to the scenario that I just described. Okay, so this is our galaxy. So with something like Astro H, if you look at the left-hand side of a galaxy, somewhere around here, okay, this is showing you the spectrum, what you expect. Okay, if it's astrophysical emission, so some kind of baryonic emission, it will be shifted to left, so it redshifted, okay, and you will have a narrower line profile due to the gas temperature being cooler. If it's dark matter emission, okay, the central of the line will be shifted to right-hand side, so it's blue shifted. And also you have a wider emission line profile. Okay. Now, of course, you can say, okay, I don't really know in prior, right, precisely the mass of the dark matter, so I don't know the central position. If I only see one line, how do I know whether it's redshifted or blue shifted? Okay. So the powerfulness of this method is that you only need to do two observations. Okay. If you look at the left-hand side of the galaxy, the dark matter line is blue shifted. Okay, so it goes in here. But if you look, then you do another observation towards the right-hand side of the galaxy, the whole scenario will be flipped. Okay. So the dark matter line will then be redshifted. Okay. So you can see the dark matter line shift follows this profile. And all astrophysical emissions, because it follows the co-rotating motion of the baryonic matter, all astrophysical line emissions follows the opposite trend. Okay. So that means, okay, with a high resolution line detector and using our basic expectations of how dark matter move in our galaxy and how baryonic matter move in our galaxy. Okay, with just a few observations to map out their relative motion relative to us, we can potentially cleanly give a very clean detection, okay, using their velocity profile. And so this result, we obtained it with a very simple galaxy model. Okay, I'm just going to show you that it's shown to work when compared with a baryonic n-body simulation results. Okay, so in this work. So just to summarize, okay. So for a very long time, right, people say dark matter producing a line gives you a very smoking gun signature. But at least from the lesson of 3.5 kV line, in X-ray energy range, it's not enough because there's many potential contaminating astrophysical line emission. Okay. So a smoking gun is not enough. But with velocity spectroscopy, okay, it gives you an extra handle to diagnose the line, whether it's a astrophysical nature or a dark matter nature. Okay. And potentially we can do that very, very soon with the next generation X-ray detector. So this is in X-ray. Okay. To do that, you need a 10 to the minus 3 energy resolution, and it's not an easy task to achieve. Okay. But in the gamma ray energy range, the only experiment that I know that can potentially do this, it's a instrument called HERD, High Energy Radiation Detector. Okay. It's sensitive to photons and electrons with a similar energy resolution, and it's expected to launch in 2020 something. Okay, and put it in the Chinese space station. Okay. So maybe this method can also work in the gamma ray energy range. Okay. Then if you remember, quite a few years ago, there was also this excitement with 133 GeV dark matter line detected by Fermi. And this method could work as a diagnostic tool. Okay. All right, so I don't have much time left, so let me skip this. Okay. Now, this is the sterile neutrino parameter space that I showed you at the beginning. Okay. With the latest results from xmm-newtons, they sort of cover half of this white space, down to around 13 keV. Okay, so they cover around here. So there's still a bunch of white space one really want to probe. Okay. So I'm going to tell you how we try to cover all the remaining white space in the hard X-ray range with an instrument called Nuclear Spectroscopic Telescope Array, okay, NuSTAR. It's a very tiny X-ray mission compared to the others. Okay, in fact, it's launched on an airplane on a missile. Okay, compared to a normal launch in a rocket. So this shows how tiny it is. So NuSTAR has a special design. Okay, right after launch, it was in a very compact configuration. Okay, but in space, in orbit, it has a mechanism that slowly extends a structure out. The reason they want to do this is they want to increase the distance between the mirror, which is the thing that's extending out, and the detector here. Okay. Because they want to increase the focal length to actually reflect hard X-rays. Okay. So thanks to these results, NuSTAR is able to detect hard X-rays, so higher energy X-ray photons, much better than existing instruments. Okay. So it's reflected in this plot showing you the effective area as a function of energy. So all the existing X-ray instruments, xmm-newton, Chandra, etc., they all got a cutoff at 10 keV because their mirror cannot reflect higher energy photons. But NuSTAR can do that. Okay. So that means NuSTAR is the perfect tool to cover the remaining part of the parameter space. Now, there's one more advantage of NuSTAR that we realized after we started trying to use NuSTAR to search for dark matter. Okay? Because its design is open, okay? That means photons can actually directly enter the detector without passing through the mirror. Okay? So we call these zero bounce photons because they do not pass through the mirror. And once we studied, we look at how these detectors, how they can view the sky. Okay? We can see that they have a viewing shape like this. Okay? So they can see the sky that's not being blocked by the not reflecting part of the mirror. So which is this part. Okay? We call this, so these few views are the skies that these detectors are sensitive to. And we find that they kind of look like a Pac-Man. So we call these the Pac-Man views. Okay, so back in 2016, we took one of the observations of NuSTAR looking right at the galactic center. Okay, so NuSTAR has two detectors, and if I plot it, how this NuSTAR particular observation, what sky area it is sensitive to, we find that it's like two Pac-Mans, okay, crossing each other. Okay. So this is the actual area that our observation is sensitive to. Now, using these photons, okay, that directly enters the detector has a significant advantage. Okay. So although without using the mirror, okay, we get a smaller photon collection area, but we are sensitive to a much larger part of the sky. Okay? So our field of view changed from a 0.1 degree square to a few degrees square. Okay? So in effect, because dark matter emissions, it's more diffuse, it's not a point. Okay? So this allows us to see more dark matter emissions altogether. Okay? So it significantly enhances NuSTAR as a dark matter detection tool. So this is our 2016 analysis using galactic center. Okay, and this is the spectrum. So I'm not going to bore you with the analysis details. And we did that, and then in 2019, we look at the M31 galaxy. So this is M31. Okay. Then for this analysis, we have several observations. So you can see the Pac-Man fields. It circles around the Andromedan galaxy. Okay. Then our latest work, it's also in 2019. Okay, so this is a very special work because we specifically asked for applied for observation time at 2 locations in the Milky Way. These are chosen such that they are as close to the galactic center as possible. Okay, but without any astrophysical source to contaminate our data. Okay, so this allows us to get a very, very good description of the data using our background model. Okay. So I'm going to just all together show you what we got with these 3 observations. Okay, so they are the purple, blue, and the red. Okay, so these are from our 3 analysis on the galactic center, the M31, and also the galactic halo. Okay, so if you remember what I said, the remaining parameter space of sterile neutrino diameter, sort of there's still a white area about 13 keV. So here. Okay, so with our NuSTAR work, we cover a lot of the remaining space, maybe except perhaps a tiny pocket in here and here. Okay. So, and we're not stopping here. Okay. Hopefully we can test the full parameter space. So one thing we're working on right now is we use almost all of the available NuSTAR data, about 50 megaseconds of it. Okay. We're working with the collaborations to get an improved background model to potentially extend the energy range. And the goal is with this, maybe we can cover all the remaining parameter space. So that's one thing to look forward to with NuSTAR. Okay. And there's actually another instrument that should be excited. Okay. Especially got into news recently. Okay. It's a mission called EROSITA. It's a European X-ray mission. It's a different kind of mission from all the instruments that I just described. It's an all-sky surveying mission. Okay, so if there are cosmologists here, you can imagine this is like the CME version, but in X-ray. And so why it's very nice, because it's the EROSITA is the first all-sky X-ray mission since ROSAT launched in 1990. Okay, so this was a ROSAT X-ray map. Okay. Combined in 3 energy bands in X-ray. Okay. And EROSITA has been launched, and this is a preliminary data from what they showed in June 2020. Okay. So after 30 years, we finally have a new version of the X-ray all-sky map. Okay. This is from 0.3 to 2.3 keV. So compared to ROSAT, the old mission, EROSITA have a decent energy resolution, and this is very important to look for diameter lines. So in this paper that we put up a couple of months ago, okay, we sort of do a mock analysis using what we know about EROSITA, and we estimated what it can do with a all-sky, angular, and energy likelihood analysis. So we take into account both the energy information and angular information. Okay. Although we did it kind of in a simple background assumption because there's no real data for us to play with yet. But what we find is quite promising. This is the expected sensitivity band. Okay. And potentially with EROSITA, we can cover also these higher hard X-ray range diameter parameter space. All right, so to conclude, okay, what I'm trying to tell you today, thanks to a series of recent developments, okay, I think the 3.5 keV diameter interpretation, although it generated a lot of excitement, is starting to be in question. Okay, so unless there's other new evidence, I will be a bit cautious on the simple diameter interpretations of 3.5 kV line. Of course, maybe for not so simple diameter models, for example, axion-like particles, it might still possible to explain both the galaxy clusters as well as the non-detections we find in the Milky Way. Okay. So in the near future, okay, I should correct this. We have a very exciting instrument called CRISM with a high energy resolution detector on board. Okay. Maybe launched in 2020 to 2022 to 2023. Then it can perform a new kind of diameter line search using velocity information. Okay. Also in near future, from our group, we hope to use NuSTAR to cover the remaining parameter space of sterile neutrino diameter, especially under the new MSM framework. Okay. So we want to sort of put the whole new MSM framework into test. Okay. And Eurosita has been launched. Okay, the last all-sky surfing instrument I described. Okay, it can potentially yield exciting results. Okay, once all the data are becoming available. Okay, even without all these near future developments, there's a planned flagship X-ray mission from Europe called Athena. Okay, so it will have a giant X-ray detector and also very high energy resolution. So this, in my opinion, would be the ultimate X-ray line diameter searching tool. Okay, but it's still quite some time away. All right, so that's it for me today. Okay, so are there any questions?
Thank you. Thank you for that very interesting talk. Yeah, let's have some questions. If anyone has something, please just shout out. If not, I will go first. I guess I maybe wondered, first of all, with this, the xmm-newton blank sky observations, this sort of revamped analysis,
Yep.
What's been the response to that from people like Bulbul and Abazagian? Have they accepted now that there is not an obvious 3.5 kV line from the Milky Way, or what's been the status since this recent one?
Right, so you're probably talking about this one that came out a few months ago. I have not heard anything from the opposing side yet. Okay. Yeah, and to me also, it fixes a lot of the problems from the previous one. Okay, so you can see, right, their actual results is more in agreement with the corrected results from the previous paper. Mm-hmm. So in my opinion, I think this is it's more robust. Yeah. Yeah. I haven't heard anything from the opposing side. And personally, I cannot think of an easy argument to say what's wrong with this analysis.
Yeah. Okay. Yeah. I also I don't really know much about Athena. What energy range is Athena planned to cover?
Right, it's similar to xmm-newton. It's in the soft X-ray energy range. If you're talking about the high resolution parts. Yeah.
Okay.
Yeah.
And do you expect that to be a high enough resolution to do this velocity spectroscopy thing you were talking about?
Yeah. It will achieve 10 to the -3 energy resolution.
Yeah, that would be exciting.
Yes.
Does anyone have anything they want to quickly jump in on?
Can I ask just for one quick question for clarification for someone who is not the expert in that area?
Yes, please.
So here you have those soft X-rays, right, where you basically have that low masses. So basically that should mean that the energy of the X-rays is also small, right? Because the sterile neutrino.
Right, so half of the diameter mass. Yeah.
Yeah, and in there, so you said that, sorry, in those new experiments, they extended it to higher energies. Is that right?
Right. So there's the typical X-ray instruments, for example, like these ones, okay, the more traditional X-ray telescopes. So they have the mirror and the detector in the same setup, okay? So that means they have a short focal length. So hard X-rays cannot be focused by these mirrors, okay? Just by design, okay? So they are not sensitive to hard X-rays, okay? And that's why with a new design from NuSTAR, okay, that looks like this, okay? So hard X-rays, it just directly enters the detector, okay? Or it can pass through the mirror with a long focal length, okay? That allows this to detect hard X-rays.
Okay. So which experiments give that constraint at at larger dark matter masses, sterile neutrino masses? That's
So
basically what I didn't understand properly. So those experiments, they are basically coming from the low end. Is that correct?
Oh, sorry.
So yeah, if you have that plot with that green exclusion curve, or this one here, for example. Okay.
Right, this one.
There it's there.
Right. Okay. So all these colored ones comes from NuSTAR with just a different analysis. Okay. Yeah. And here these are some other kinds of detector that I didn't have time to talk.
Okay. So I think I got confused because I saw those at much larger masses and which.
Right. Right. So for example, Integral is a soft gamma ray telescope. So it's another different kind of design. Yeah.
Okay. Thanks a lot for clarifying this.
If nobody else has anything to ask, so thinking about this parameter space. So say you close up the remaining white space. And I mean, suppose I'm somebody who really wants sterile neutrinos to exist. What do I have to do in terms of the model dependence to give me more white space to work with?
Right. Right. So you have to give up resonant production mechanism. Yeah. Right. For example, the sterile neutrino can come from some kind of heavy scalar decays. Okay. Then the production mechanism is no longer tied to the mixing angle, right? Then you can, you can probably make it work down here.
Could I go arbitrarily small? I mean, at the risk of fine tuning? Or?
Right. So that I'm not really familiar with, right? So people like Kusenko, and they probably know much more than me.
But there may be some way out just by going to smaller mixing angles if you close that gap. But
you have So the nice thing about resonant production is that you don't have to introduce another set of new particles to talk to sterile neutrino, right? Yeah. So you can fix that by adding new particles.
Okay. Yeah, if you decouple the production from the oscillations, then you can set theta to 0. There is no constraint.
Exactly. Yeah.
Cool. Well, I think if anyone has anything else, they can jump in. I'm going to stop the recording.